Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, word break 2. I think we did the first one at least like 3 or 4 years ago, so finally able to do the second one. We're given a string s, which is kind of a sentence, right? And we're also given a list of words that we can choose from in a word dict, that's what it's called, though it is given in the form of a list, so keep that in mind. But overall, the premise is similar to the first word break problem, where we're trying to break this sentence up into words that are given to us in the second parameter. So let's just try to think about this in the worst case. So if we were trying to brute force it, there's actually two different ways that we can brute force this. Suppose we're starting with like this first example. Starting from the beginning of the string, we could try every single substring starting from here, right? So just the letter C itself, does that exist here? Nope. Does CA exist? Nope. Does CAT exist? Yes, it does. It's here. So in a sense, that's kind of one branch over here, cat. And if we were to choose that word, where do you think we're starting after that? Well, we've used these characters, so now we're at this S character. We'd continue down that line of thinking. S is not a word, SA is not a word, SAN, nope, but SAND, that forms the word sand. So going down here, we have the word sand. And then we've done all this, and then there's three characters remaining. D is not a word, DO is not a word, and DOG is a word, so we'd get dog. And there aren't really any other choices from here, right? And from here, there weren't really any other choices as well, though I think there could have been. But there was a different choice from the root. We actually could have had the word cats as the first choice. So down the other branch, that's what we would have had. And if we chose that, then the following words could have been different. We would have had the word and the word dog. But basically, the idea is that this is kind of a decision tree. This is one way to brute force it. Basically, check every single substring from wherever we're currently starting at and check if that is a word in here. Some of the paths may not necessarily lead us to a result. Suppose that the word sand did not exist. Suppose we chose the word cat to start off with. Okay, then we're over here. We're never going to find a word that starts with S from here. Like none of these substrings are ever going to be found in this word dictionary starting from that position. So that could have been like a dead end in our decision tree. So while I'm not going to draw out the entire thing, maybe you can do that if you'd like to. Just try to conceptually understand what's going to go on in that decision tree. That's one way to do it. The other way to do it, let's say we're starting from here, we could check. Instead of every substring from here, we could just go through every single word. We could check, okay, does cat kind of fit in here? Starting from here, does cat like form the substring? In this case, it does, but suppose it didn't. We would have then checked the next word, cats, and that one also does. So in a sense, that's like our two branches, right? Cat and cats. You might prefer doing it this way. And I think that's perfectly reasonable. I think this is kind of more simple in some ways. From the other branches, we can continue. We would then, let's say, be from here. We would check, okay, do any of these words fit? Cat doesn't, this one doesn't, this one doesn't, but this one does. Sand does fit there. We would then start from the remaining portion. Now, the only thing is, which one of these is going to be more efficient? At first, it might seem that they're both going to be equally efficient. But if you were to scroll to the bottom of the problem, quickly skim over the constraints, you're going to find that the length of the input string is going to be at most 20. So every time we're branching, right, like 20 different directions in the worst case, suppose every single one of those substrings was a valid word, we'd have 20 branches in the worst case. The other thing is, if we were to do it based on words, well, the length of that data structure is going to be 1,000. So I guess technically in the worst case, we could have 1,000 different branches. But now that I actually think of it, I guess I lied. And I guess they actually both are equally efficient in terms of big O. Can you kind of guess why? Because if we have 1,000 words and we only have 20 characters in the input string, unless we have duplicate words, there's no way we're actually going to have 1,000 branches. Also, think of it in the worst case, like how many different sentences could we form? Like if literally every single one of these characters was a word, how many sentences could we form? Well, I guess every character gives us a choice. We can end the word here, or we can not end the word there, in which case we would have like a branch, like suppose we have C and then we have CA. And so it's kind of just two branches every single time. From here, we'd have A and then maybe whatever the next character is. Basically, what I'm getting at with all of this is that the time complexity is going to depend on the size of the output, right? How many different strings can we actually create in the output? And basically what we're trying to do is choose where we put a space in the input string. And it looks like we have a choice. We can put a space here or we can not put a space there. Suppose we did have that choice, and we'd have that choice for pretty much every character in the input. So the overall time complexity is like two choices. The height of that tree is going to be n. N is the size of the input. So overall time complexity is going to be 2 to the power of n. So that was kind of a long-winded explanation of saying it doesn't really matter how we solve the problem. Knowing that, I'm going to go ahead and choose the approach where we start with every single substring starting from the beginning, because again, we have to build the entire output. There's no shortcuts for that. There's no optimization we can really make that's going to change the overall time complexity of this, though I will show you a small optimization. We can technically add memoization to this. It won't change the overall time complexity, but in some cases, it will make the solution more efficient. So the easiest way to solve this is just with the brute force backtracking solution. We're only going to keep track of the index that we're at in the input string S. I'm actually not going to do the base case quite yet because there actually is something else we're going to keep track of. We're just not passing it in as a parameter. And that's going to be what the current words are so far, the current words that we've formed. We're also going to have a result, which is ultimately what we're going to return. And we're going to call backtracking starting from the beginning of the string. So we're going to pass in 0 as the index. So what we're saying is we're at index I. We want to try to form every substring starting from index I. So we're going to say for J, in range, starting from index I, going up until the end of the string. And we're going to say, this is the word starting from there, I up until J. We put a +1 here because in Python, the ending index is non-inclusive. So +1 is basically going to end at J. We want to know, is this word in the word dict? Now, technically that's a list. So we can make it a set if we want to speed things up a bit. So I'm going to go ahead and do that over here. Now this will be a constant time operation. Well, I guess it'll depend on the length of the word, but I think all the words are pretty short in this case. So is the string. It's only about 20 characters at most. So we'll check, is this word in there? If it is, we want to backtrack. Guess what the starting index is going to be? If our word ended at J, we probably want to start from J plus 1 then. Okay, but isn't there something we should be doing here? Current is going to be the words that we've added so far. Right now it's a list. So that's what we're going to do here. It's easy enough. Current, append the current word. After we're done backtracking, go ahead and pop the current word. Now, what is the base case? What's the base case going to be? Well, once we reach the end of the string, so I is equal to the length of the input string S. And of course, we're going to return from here, but shouldn't we be updating the result as well? And how do we update it? Should we just say result.append the current list of words? That's not what we want. We want to take those words and have a space in between all of them. Instead, we can do in Python pretty easily, take the space character and then join the current words with the space as the delimiter, and this will form a sentence that we can append to the result, and then that's what we're going to end up returning. This is the entire solution. It's pretty easy enough, I think. As you can see on the left, it works and it's pretty efficient. Now, why would we want to add memoization to this solution? In the worst case, it's still going to be big O of 2 to the power of n. Now, in most cases, it's not going to be that inefficient. It really isn't. When you look at it, there's not going to be that many choices. But there is one example where it's going to run pretty poorly. Let's try to think of an example where it would run really poorly. Suppose we're given a string which has a bunch of characters that are the exact same. And our list of words, like we're going to have a bunch of choices. Like we're looking for the most inefficient solution where we're going to have branches every single time. Every single one of these substrings is going to exist in the word dictionary. And obviously, when the character is the exact same, that is a case where that's going to happen a lot. So just assume we have this and assume we even have 5 X's in a row. So now the decision tree would look like this. We can choose an X. We can also choose 2 x's. We can also choose 3 x's and 4 x's and 5 x's. And then obviously from here, we could then have 4 branches, like basically these 4 branches. So I'm not going to draw all of them out, but this is going to have 4 branches. This is going to have 3 branches. This is going to have 2, and this is going to have, I think, just 1. But this is obviously a base case because we have the entire string. So this is very inefficient. Why is it inefficient? I guess the only way to really know is to kind of draw it out. So I'll do a little bit of that. Notice that along this path, suppose we have 1x and then 2x's here and then 3x's and then 4x's. So I'll kind of put a little line under them to separate what's what. Suppose we're solving this recursively. Suppose this is the first branch we go on, because the way we've coded it up, this is the first substring we're going to look at. We're going to see, okay, it exists in the list of words. So then solve the remaining subproblem. Now, doesn't really matter. Caching isn't going to change the big O time complexity, but it's actually going to be very effective to optimize this particular problem. Because watch, right now we're going down this part. Here we were at index 0. Here we're at index 1. Here we're at index 2, because when we have 2 characters done, we're going to be over here, right? So that's my reasoning. Here we're at index 3. Here we're at index 4. Here we're at index 5. That's the base case. Here we're at index 2 because we have 2 x's, right? So here we're going to be there. And then here we're at index 3, here we're at index 4, here we're at index 5. Once again, base cases out of the way. Do you notice anything about this? Remember, what determines a subproblem in this context? Basically just the index that we're at. Because what we're asking is, what are all the words that we can now form starting from this index with the remaining characters? Or rather, what are all the sentences that we can form? Sorry for misspeaking, but that's what we're asking, right? From here, what are all the different sentences that we can form? Because once we have those sentences, then we know all we have to do is append this to the beginning of them. So that's the subproblem. The subproblem is get the sentences starting at index I. That's the subproblem we're trying to solve. It looks to me, when we go down this path first, we're going to solve this subproblem, this subproblem, this subproblem, and this subproblem. It also looks to me that this subproblem is repeating. This subproblem is repeating. This subproblem is repeating. Now, this is the base case, so I guess it doesn't really matter, but that repeated as well. So why not cache the result of these, and it'll speed this problem up, because then we won't have to recompute a bunch of work from here, here, and here. We will still have to build all of the possibilities, all the possible sentences, but we won't have to do like exponential work from here. We won't have to deal with the overhead of recursion and all that stuff. So this will optimize the solution if we were to add caching this way. Now, the only thing is that coding this up is going to be a little bit different than the way we did it before. We are going to have to rely on the return value, because that's what caching does. It cares about what the return value of a problem is. The augmentation I'm going to make to this is, watch. From here, let's start with the base case. Here, we're going to say that, like, starting from there, when we're out of bounds, what are all the sentences that we can form at that point? Nothing. So what I'm actually going to do, though, instead of returning an empty array, I'm actually going to return an array with an empty string, because then we're going to take this. This is the word that we had, 5 x's in a row, and we're going to add that with this empty string. So then we'll have a string with 5 x's. Okay, from here, what I'm going to do is end up returning, you can probably guess, it's going to be an array with just one string. It's just going to have a single x, because if we used 4 of the x's and we just have 1 x remaining, what are all the sentences that we can form? Just a single x. So from here, we're going to then add the 4 x's with that single x, and we're going to get a sentence that looks like this: 4 x's, a space, and then 1 x in between. I'm going to keep going for a little bit. From here, we're going to get what are all the sentences that we can form with these 2 remaining x's. That's the subproblem. What is the result of the subproblem? It looks like this. We can have 2 x's in a row, or we can have 1 x, space, and then 1 x. So now what I'm going to do is take this string, 3 x's in a row, and append it with this, and append it with this. And the result will look something like this: 3 x's, space, 2 x's, 3 x's, space, x, space, and another X. So it's just going to be a loop. It's going to take the return value and then it's going to loop over all of them and then append this to the beginning. I guess I shouldn't really use the word append because appending is usually at the end. So sorry for misusing that word. But this is the idea of what we're doing, and then we can do this recursively. So I won't kind of keep going through this, but again, if it still doesn't make sense to you, you can use the logic I was talking about and kind of continue with the rest of the decision tree. Again, the overall time complexity in the worst case is not going to change, but this is an optimization that we can make so that certain examples will run more efficiently. Now let's code it up. Okay, so we're not even going to worry about the cache right now. We're actually just going to focus on the backtracking. Starting at index I, same thing as before. This is what we're going to use to cache. Now we're going to change the base case a little bit. When this is the end of the string, we're going to return an array with one empty string. That's the base case. Otherwise, we're going to try to actually build the strings. One thing about this is we could put some like sentences in here. Like that's what we're trying to do. But it could be possible that like given the string that we have, suppose the string is something like cat, dog, ABC, I don't know. And suppose that the words that are given to us are cat, dog, but no ABC. Maybe the other word that's given to us is dog ABC. So one way to validly split this up would be cat and then dog ABC, right? But suppose you took another path. Suppose you tried to say, okay, cat, and then use the word dog. Okay, great. Now you're here. You have these two words. You're trying to fill in the rest of the string, but there's no word for that. What would we return in that case? We weren't able to break the string starting from here. Like these words are built so far, but now we're at this point. That's where our I pointer is. We can't complete the sentence. In that case, we return the empty array. So just keep that in mind. There is a distinction between the empty array and the base case, which has an empty string. This implies we were able to fill in the entire sentence. An empty array implies we were not able to do that. So I'm very specifically returning this. There are other ways you can code this up. This is the way I'm deciding to do it. And if you prefer to do it a different way, that's perfectly fine. But now let's actually do the logic. So it's mostly going to be similar to what we had before. We're going to have that same exact loop for j in range I up until length of s. We're going to get that same word starting from I to j plus 1. We're going to check. This time, instead of checking if the word is in the word dict, which let's create that set again. So up here, I'm going to transform word dict from a list to be a set. But here, instead of checking if it's in that, I'm actually going to check if it's not in that, because if the word does not exist, we're going to continue to the next iteration of the loop. Why am I doing it this way? Basically, so that we don't have to keep nesting like 5 times in here, because we're going to have a couple more things going on. Okay, now the backtracking. All we do, again, pass in j plus 1. The result of this, though, is now going to be relevant. It's going to be a list. It could be an empty list. It could be a list with an empty string, or it could be a list that has some actual sentences in it. So we're going to call this strings. Now, it's possible that it's empty. Remember, if it's empty, we were not able to fill in the remainder of the string. What do we do in that case? Well, I'm going to say if not strings, continue to the next iteration of the loop. There's nothing in there for us to do anything with. Otherwise, if this does not execute, we know either it has some real words and sentences in it, or it has the empty string. So this is what we're going to do. For substring in that list of strings, this is probably a bad word to use. I don't know a better name for it. They say naming is the hardest thing in programming for a reason, I guess. But here I'm going to say that right now our sentence is just the current word that we started with. And I'm going to say if the substring is non-empty, then take the sentence and append to it an empty space plus that substring. Why am I doing this? If you're clever, you can probably figure it out, but I'll go ahead and tell you. If we return an empty string, then the sentence does not change. We definitely don't want to add a space to it. That would just mess things up. But if we were given a real string in that return value, well, then we definitely want to separate the word and this by a space. That's why I'm doing it this way. Again, there are other ways to code it up if you want to. This is the way I'm doing it. Now, after that's done, let's go ahead and take the sentence, append it to the result like this, and then outside of this giant loop, we're going to return that result. Now you can probably see why I have these continues, because otherwise we're going to end up nesting pretty far in. In terms of how we actually call the backtracking function that we just wrote, pretty easy, just start at index 0. How do we add caching to it? That's also pretty easy because we've set this up pretty well. If you were to try to add caching to the previous solution, it would not work. The return value matters for caching because with a cache, we always return whatever happens to be cached, like this. If I is already in the cache, then we're going to return the list of sentences that we could form starting from index I, which is already cached. If it's not already cached, once we have those sentences in our result, we're going to make sure to add them to the cache before returning. This is the entire code. Let's go ahead and run it. And as you can see on the left, it works, and it looks like it is a little bit more efficient than our previous solution was. If you found this helpful, check out Leetcode.io, like and subscribe for more, and hopefully I'll see you soon.